Okay, exam 3 is coming up. It is Thursday, 4:10. And then if you want to take it with the night class instead, that's Wednesday, 4:09. And the topics are going to be just, there's only going to be 2 of them, thermodynamics and electric fields. So just 2 sets of practice problems. And this problem set, for the people who didn't take my class last semester, this problem set is not something that you need to, like, it won't really help you get ready for the test, except in a very like abstract way, make you work on these topics and stuff. But the practice problems are the ones that are relevant for the exam. So okay, and then there's also no lab the week of the exam. So that is right. And that's, what would be that Monday, 4/7? So no labs that week. But like always, you're welcome to come in. Yes, that's what it's for. That's what I should say, makeup labs. So, well, you don't really make up the labs, so that'd work okay. I mean, it's really just sort of simulated labs with worksheets for the makeup lab. So yeah, come on in and we can do that. But you can miss one lab without it affecting anything. So, so if you haven't missed one yet, and you just know you're going to miss one, you can just miss it, and it's not a big deal. All right. Anybody have any questions about anything coming up? Or any questions about what we've been discussing? All right, so now we're getting into electric current. Yep. We finished, yeah, we talked about electric fields and capacitors. Yep. I think if there's a problem on capacitors on the practice problems, then yes, I think there is, but if there's not, then you don't have to do it. Okay, so electric current. When you talk about electricity, essentially means electric current. So anything that runs on electricity needs to have electric current to run. That's what makes it run. So electricity essentially means current. And what current means is the motion of charged particles. That could be any charged particle. Like you could have electric current by having balls of positive 5 coulombs, flying through the air. That's an electric current. But practically speaking, that's not how we make electric current flow. So generally speaking, electric current comes from the motion of electrons. And those electrons are hopping from one atom to the next atom. So from one atom to another in a conductor. Positive charge or positive current is in the direction of positive charge motion. And there's really no such thing as positive charge motion, you know, since electrons are what are creating the current. And so what we really have, it's sort of this backwards thing with our sign convention. If you really tracked what particles are moving to make electricity flow, really electrons are moving this way, and that makes positive current move the opposite way, okay? So it's really like the absence of electrons. As an electron hops this way, it makes this side more positive because it's losing a negative, and that makes current flow this way. The electron goes one way, the current goes the other way. And that has to do with just the convention that was chosen before people knew about protons and electrons. If you have like a piece of a conducting wire, then at some cross section, you're measuring the motion of positive charges across this chosen location in a conductor. And this direction is the positive charge. That means this is the current direction. Okay, and so even though it's electrons that are moving, you should think about it as the motion of positive charges, because that's just how the math works out. Okay, one thing to notice then is, no, first let me give you a definition. So the current, and think of this location as the location P, okay? Then the current, and we'll abbreviate that as a capital I. I'm not sure where that comes from. At P is the amount of charge going past that point T, that point P, divided by the time, the amount that crosses P in the direction of the positive charge. Okay, so now one thing to notice about this, and this is a really important thing, and it seems like no matter how much I mention this, I'll mention it sort of over and over, there are always going to be some people who don't do this, you know. So if you don't follow this requirement, you're going to lose points. So don't be the person who ignores this. Current has a magnitude, and its magnitude is calculated as this amount of charge per unit time, but it also has a direction. So if you don't give both in questions about current, you're going to lose points. So if you don't give both when you're asked for the current, you'll lose points. The SI units of current. So based on that definition I gave above, what are the SI units of current? Well, what are the units of Coulomb? Coulombs are the unit of charge. And then what are the units of time? Seconds. So it's going to be coulombs per second. And that's given its own name, amperes. People don't tend to say amperes. They usually just call it amps. Ampere was a guy's name. And it's abbreviated as a capital A. Here's sort of a rough guide to the size of an ampere. The danger of electrocution from an electric shock starts around 1/10 of an ampere, 0.1 amperes. Okay, so 1/10 of an ampere is a large amount of electric current for us. To start a car requires about 300 amps. So, you know, I don't know. Those are sort of two ballpark things. The shock that you get from like an electric socket is considerably less than 1/10 of an amp. It's closer to like 100th of an amp. Okay, so now current is the thing that powers devices. Anything, when you talk about electricity, you're talking about electric current. But what causes electric current? There's sort of, these two things are sort of tied together in a way that can be kind of confusing. So current flows when charged particles are free to move in the presence of a potential difference. And that's, you know, potential difference is just another way of saying voltage. So a current flows when, first of all, those charged particles, the electrons, are free to move. That means that they're in a conductor of some kind. And they're in the presence of a voltage. And remember, voltage is just a way of representing like an electric field, some kind of force field. So it makes sense, you know, like if there's a charged particle that's in the presence of electrical forces and it's free to move, it's going to take off. Forces make it move. And when those particles move, that creates electric current. Okay. And so the way that we're going to talk about forces making these charged particles move is we're going to talk about the voltage, the potential difference from here to here, okay? Current always flows from a high electric potential to a low electric potential. In other words, it flows in the direction of a voltage drop. Okay, so a voltage drop just means that in that direction, you have a lower potential on this side and a higher potential on this side. So, for example, say you have a battery. This is the plus, this is the minus. Let's say this is a 9-volt battery. And you hook up a wire here with some electrical element here. Excuse me. Thanks. And a wire connected over here. Well, what this means is the high electric potential is on this side. That capital V is electric potential. Over here you have a low electric potential. And so which way is electricity going to flow? Well, the electricity would love to just take the shortcut and go from the positive to the negative inside the battery, but the battery doesn't let that happen. And so the positive charge recognizes that if it goes through this long path, it can get from a high potential to a low potential. And so current flows through this wire, flows into the element, which is whatever electric device you have, a light bulb or something, powers the device, and then ends up at the negative side. Okay. So that was talking about last week, insulators. Oh yeah, that was in a capacitor. Yep. And so there's the same thing in a battery. In a battery, so like if you had the two halves of the battery connected by a conductor, then the battery wouldn't work at all because any positive charge that built up would just flow right over to the negative side. So what you have to have is some kind of insulator, similar to the idea in a capacitor, to keep the positives over there, the negatives over here. And then when you give them a path to go, that positive charge rushes through the path to get over to the negative side, to go to a lower potential. This is going to be our first look at a schematic diagram. So if you look at that picture on the left, we would represent this in a schematic this way. We'd have a battery connected to wires, connected to, well, we don't know what kind of element this is, so I can't give any more specifics about this, but whatever element you have would be represented by some schematic symbol. Then wires and connected over here. Okay. This would say 9 volts. And in this element, the long line in the battery symbol is the positive side, the positive terminal, and the short line is the negative terminal. Okay, so here are some things to know about schematics. And I'm going to mark a couple of points on this schematic. So let's call this the point A, this the point B, this the point C, and this the point D. And here are a few important facts about schematics. First, current always flows from high potential to low potential. I guess that's the one I just gave a minute ago. Second, any 2 points in the schematic that can be reached without crossing an element and for us the elements are batteries, capacitors, and resistors, which we haven't talked about yet, but we will today. So any 2 points in the schematic that can be reached without crossing an element have the same electric potential. So in other words, look at A and B, okay? The points A and B. You can go from A to B if you go this way, then you go through 2 circuit elements, right? But you can go the other way. There is a path you can choose where you can get from one to the other without passing an element, just going across the wire. And that means that A and B have the same electric potential, okay? Same with D and C. It doesn't matter that you could take a path through elements. You have the choice to just take a wire from D to C or from C to D. So those have the same electric potential. B to C, though, there's no way to go from B to C without crossing the element here or the battery if you go the other way. And so B and C have different electric potentials, okay? So, for example, in the picture above, the potential at B is equal to the potential at A. So that's what I just talked about. And what that means is if you take a potential difference, VBA, okay, so now this potential difference is a voltage. If you're trying to find the voltage between A and B, you would do it by taking VB minus VA, and that's 0, okay? So there's no voltage going to B from A. There's also, you know, if you wanted to calculate the voltage going to A from B, you'd have VAB is equal to VA minus VB. That's also equal to 0. And we also saw that VD is equal to VC. So VDC is equal to VD minus VC, and that's also equal to 0. Okay? And 3, so the last important fact about schematic diagrams is in the schematic, you can shrink, stretch, or bend any wire without changing the meaning of the schematic. So for example, this schematic, the one I just drew before, is equivalent to this, okay? All I've done to get from here to here is stretch some wires, bend some wires, okay? All that matters is the relationships between the elements in the schematic, okay? So, for example, now if I did, say this was element 1, this is element 1, okay? And say that now I put an element 2 here, okay? And put element 2 here, okay? Now those two wouldn't be equivalent because in this schematic, the positive terminal of the battery, current leaving the positive terminal of the battery gets to element 2. In this one, positive current leaving the positive terminal of the battery reaches element 1 first. So those aren't equivalent anymore, okay? To do these, I did more than switch, than just bend and stretch and shrink wires, okay? Any questions so far? Yeah, sure. Okay, so now I'm going to talk about the last type of circuit element. And that's resistors. I mean, it's not the last type of circuit element in the world, but the last one that we're going to deal with. You can think of resistors as impeding current flow. You can think of them as sort of like electrical friction. And in fact, there's a lot of ways that it's really similar to friction. When there's resistance in a circuit, that generates heat. And if there's enough resistance, it generates light. And that's just energy being stripped out of the system, the same way friction strips kinetic energy out of something. It's energy that isn't being used for anything. It's just being dissipated. It goes away. You'll never get it back. The SI units of resistance are volts over amps. And that also is given its own name, ohms, named after another scientist, Ohm. And we write that as the Greek letter omega. like a horseshoe. I think that's a capital omega. And resistors obey Ohm's law, which says this. You may have heard this before somewhere in passing. The voltage is equal to the current times the resistance. But I have to tell you strictly what all of these mean. So V is the voltage across the resistor. So in other words, that's the potential difference between the two terminals of the resistor. The current I is the current through the resistor. And R then is the resistance of the resistor. And the current through the resistor always goes in the direction of the voltage drop. So it always goes from the higher potential, from the terminal with the higher potential to the terminal with the lower potential. Okay. And a resistor, let's see. In schematics, resistors look like jagged little squiggles with the resistance listed above it. So, you know, a 50 ohm resistor would look like that. So we're going to use Ohm's law to solve resistive circuits. Resistive circuits are just circuits that besides the battery or the voltage source, all they have is resistors. They don't have any capacitors or any other kind of device. And solving a resistive circuit means find the voltage magnitude and drop direction at every element. And second, find the current magnitude and direction at each element. One thing that's tricky about doing stuff with electricity is most of the stuff that we've done, even the thermodynamic stuff for the most part, everything that we did in first semester physics for sure, we could picture what would happen, like, what's going to happen if a helicopter's flying along and a ball's dropped or whatever. You have enough experience with the motion of things that you can picture that happening. With electricity, it's harder to come up with that intuition if you haven't done any wiring or anything. And so for intuition, you can, so something to notice, for intuition about circuit behavior, you can think of circuits as closed paths of pipes, like water pipes. Then voltage is water pressure. Well, really, I guess to technically be accurate about this, the equivalent of the electrical potential is water pressure. And current is water flow. And resistance is narrowing of the pipes. Okay. So for example, if we have a simple circuit like this, so there's a battery, here's the positive side and the negative side, and we want to picture what the water's going to, well, we want to picture what the electricity is going to do. You can picture it as a water pipe like this, where you have a narrowing of the pipe where the resistor, representing the resistor, and here you have a high pressure, and here you have a low pressure. Okay, so what's going to happen? The water that's at a high pressure is going to want to get to where there's a low pressure. Okay, so water is going to move this way. When it gets up here, it's going to, when it encounters this narrowing, that water is going to be sort of held up. And that's going to create, since there's a bottleneck here, there's going to be a high pressure here and a low pressure here. And this tells you everything that you need to know about the current direction, the voltage drop direction, because so current is going to flow this way, right? That's the electric current is going to flow like this. There's going to be a voltage drop pointing to the right at the resistor, and that means that we'll have a voltage that's positive on this side and negative on this side. Okay. And so if you ever get confused about what's going to happen, you can think about any problem this way, and it'll sort of help you figure out the directions of things. Anyone have any questions about that intuitive model? Yeah. Anyone want me to clarify anything about like what the water's going to do here? You follow how this example works?
So you were talking about the voltage drop.
Mm-hmm.
Voltage drop would you say occur to the right, which is maybe on the negative side, right? Or would it be?
So we would say we represent the voltage drop with a positive where the higher electric potential is, and a negative where the lower electric potential is. And so if V is 50 volts, then this says that the left side is 50 volts higher electric potential than the right side. And that means that current is going to flow from the plus toward the minus through the resistor.
How does the resistor actually work?
So what does it do? So the thinner it is, the more resistance there is. I think it's probably just how quickly electrons can move from one atom to the next. And when you buy resistors, they're just like in some kind of casing. They're just coiled up, wires that resist the flow of electrons. And so here's okay. Yeah, I guess I don't have anything else really to say about that. Light bulbs, and we're going to do a lab like this. You can think of light bulbs as resistors. It's just a thin filament. The electricity flows through that filament, and there's enough friction, enough resistance in that filament that not only does it create heat, but it also creates visible light. And that's how a light bulb works. Okay, so Ohm's law. All right, well, let's just start doing some examples using Ohm's law. All right, so let's say that we have a battery connected to a resistor. Let's say the resistor is, so the resistance of the resistor is 250 ohms. And let's say that the voltage of the battery is 15 volts. And we want to solve this circuit. So first, what does it mean to solve the circuit? We want to find the voltage and the current across each of these elements. So we need to find, for the resistor, we need the voltage and its direction. We need the current and its direction. And then for the battery, we need, well, the voltage is given, but we need the current and its direction. Okay. Okay, so what do we know about, so right now we have numbers. We have the voltage at the battery, but that's not the same thing as the voltage at the resistor. And to use Ohm's law, we need the voltage at the resistor. We have magnitudes for these. Do we know any directions on anything? Well, the schematic diagram does tell us something about the direction for the battery, the voltage drop direction. So where's the positive and where's the negative? Yeah, so the positive is at the long line, the negative is at the short line. Okay, so now we're getting somewhere. We know that at the battery, the left side is 15 volts higher than the right side in electrical potential. We also know this about schematic diagrams. whatever the electric potential is here, anywhere you can reach without going through an element has that same electric potential, okay? And so that means that, let's just, to think about it, let's think of this side as having an electric potential of plus 15, and this side is having an electric potential of 0, okay? That means that over here, we have an electric, like right at the terminal of this resistor, we have an electric potential of plus 15. And over here, we have an electric potential of 0. And so we know the voltage across the resistor, too. We know that this is the positive side, this is the negative side, and the voltage is 15. I think I always give you that. I mean, you could also do a problem like this. If I gave you the voltage of the resistor, you could figure out what the battery had to be, but I think I always give you the one for the battery. And definitely in the next set of practice problems, so the stuff we're doing now isn't on the exam on Thursday. But the next set of practice problems, all of the problems start out with the battery's voltage, and you work through it like this. Okay, so now we know the voltage. Yep.
So is that like the negative side is always 0? I mean, even though it's
You can think of it that. So remember with potential energy, gravitational. Well, I know it's been a while since you took Physics 1, but didn't you say that? Like, so in Physics 1, though, when you talk about gravitational potential energy, there's an arbitrary constant. The only thing that isn't arbitrary is the changes in potential energy as you go higher and lower. Do you remember about that? Because you got to choose where your height was equal to 0. And so if you chose the center of the Earth as the height equals 0, you'd have a very different potential energy for this pen than if you chose this as height equals 0, you know. It's the same thing with electric potential. It's the value of it is arbitrary. What isn't arbitrary is the change in electric potential. And so, yeah, you could always think of, when you have the voltage at the battery, you could always think of the positive side as being positive battery voltage, and the negative side is 0. All right, so do we know anything about the current? Well, specifically, do we know the current direction now that we know the voltage direction? We do. Do you remember what it is? Yep, that's right. The current always goes in the direction of the voltage drop at the resistor. And so the current direction is this way. And you always indicate the current direction with an arrow. And now how can we come up with the magnitude of the current? Yep. So we use Ohm's law. Ohm's law says 15 volts is equal to I times 250. So I is equal to 15 over 250, and that is 0.06 amps. And so the magnitude of the current here is 0.06 amps. If this is a circuit, that current doesn't have anywhere to go and hide, right? It can't, those electric particles can't just wait out here in the corner or anything. So if there's a current of 0.06 amps going this way into this wire, there has to be a current of 0.06 amps going this way out of the wire. And that means that the current at the battery is going. So if it's going up at the resistor, it's going clockwise 0.06 amps. Then at the battery, it has to be going clockwise also at 0.06 amps. And so that's the solved circuit.
Did you give us the omega?
Yeah, the resistance.
Resistance?
Mhm.
So to solve for resistance, why would we have to do that using the equation?
You'd have to know something else. I couldn't just give you the battery and no resistance. You couldn't solve for anything, but I could give you the voltage at the battery and the current, and then that would be enough to do it. But you do it the same way using the same equations. You just be solving for a different variable.
So we don't use B divided by A equals Ohms law or whatever. No, that's not, that wasn't.
Okay.
I thought it was.
I thought it was too, but it wasn't. Okay, so here's another one. Here, you do this one. So say you have a 9-volt battery connected to a 20 ohm resistor. Solve that circuit. See if you can work through that together.